us now look at the next problem in this series. So this is exercise 1.1.4. This question is about matrices. So it says, consider three elements from the vector space of real 2 cross 2 matrices. So what are these three matrices that we are considering? The first one is the next one, and finally the third one. So the question based on these three elements from the vector space of real 2 cross 2 matrices is, are they linearly independent? Are they linearly independent? Support your answer with details. So before we start solving this question, we need to make a note of a few points. First of all, the set of real 2 cross 2 matrices forms a vector space, a linear vector space. And how is that? This can be seen by again verifying those 8 axioms. Similarly, not only just set of real 2 cross 2 matrices, even set of complex 2 cross 2 matrices will also form linear vector space. So just for an example, let us see what the null matrix for this set of real 2 cross 2 matrices would be. So if we have, let's say, the most general real 2 cross 2 matrix would be this, where A, B, C, D belongs to the set of real numbers. In this case, if we want to define the addition, so addition for matrices is defined as following. If we have, this is the first matrix, and if we take the second matrix, the addition is defined as the following. Also, this is addition. Then we also need scalar multiplication. So scalar multiplication is defined as follows. So if we have a scalar A naught multiplied with this 2 cross 2 matrix, then what do we get? This scalar is multiplied to each element of the matrix. So this is scalar multiplication. And A naught belongs to real numbers. So this we see that for the set of real 2 cross 2 matrices, for this to be defined as a linear vector space, we need to have a definition for addition and a definition for scalar multiplication. Now with this definition of addition and scalar multiplication, we can see that the null vector or the null matrix in this case would be simply 0, 0, 0 0. So all the elements of this 2 cross 2 matrix, if all the elements are 0, then that is the null vector. So the null exists. Similarly, we can see what the inverse is. So inverse for A, B, C, D matrix would be simply minus A, minus B, minus C, minus D. So the inverse exists for each and every 2 cross 2 matrix. So we see the existence of null, existence of inverse, we have the definition for addition, scalar multiplication, and then we can easily see that all the other 8 axioms, all the total 8 axioms are also verified. Here I have just shown the example for null vector and inverse. You could work out the remaining 6 axioms for yourself. So we see that the set of real 2 cross 2 matrices would indeed form a linear vector space. So this is the first comment I wanted to make. Then before proceeding, we want to understand what linear dependence or linear independence means. So since the question asks whether these vectors are linearly independent or not, so we need to be aware of the definition of linear independence before we can proceed. So let us define linear independence. So definition of linear independence. A set of vectors, say we have a set of vectors this set is set to be linearly independent if only such linear relation as So this is the definition of linear independence. What does it say? It says that if we have a set of vectors 1, 2, 3, so on up to n, then this set of vectors is linearly independent if we look at this kind of a relation, this kind of a superposition, linear combination of vectors. If this linear combination of vectors is set equal to the null vectors, then these coefficient ai, these coefficients ai of each of these vectors I, if all of these coefficient ai are 0, then we would say that all these vectors I going from 1 to n are linearly independent. So just as an important point over here, we denote vectors by this ket notation. So ket notation, as you would have been seeing that we are using this ket notation to denote any vector of a linear vector space. So even if we are considering matrices over here, even if it is a matrix, it is being denoted in this ket notation as a vector. So coming to this linear independence, if all these coefficients in this linear combination are 0, then we say that the vectors are linearly independent. What does linearly dependent mean? If these vectors are not linearly independent, if it is not linearly independent, then that implies that the vectors are linearly dependent. This would mean that this relation out here, for linear dependence, this relation out here would be satisfied for a certain combination of AIs in which all the AI are not equal to 0. That means we could write this as, for linear dependence, we would have some vector of the linear vector space can be represented as a linear combination of all the other vectors. So we have this vector j. This can be written as a linear combination of all the other vectors in the vector space apart from j. If this relation is satisfied, then that leads to linear dependence. So this is the definition for linear dependence and linear independence. So from this we can say that for linear independence, it is not possible to write any member of the vector space as a linear combination of the other members. And if we are able to write down one member as a linear combination of the other members, then that means that those set of vectors are linearly dependent. Now we can attempt to solve the question that we have. Let us move towards the question. So in the question we have these three matrices or vectors. We need to see whether they are linearly dependent or independent. So let us try and form the linear combination of these three vectors that we have. So A times the first one, A1 times the first vector, plus A2 times the second vector, plus A3 times the third vector, and this we need to set it to the null vector. So let us write down the matrix that we have. So the first matrix is 0 1 0 0. Second matrix is 1 1 0 1, and the third matrix is -2 -1 0 -2. This we need to set it equal to the null vector or the null matrix. So let us try and solve this equation, and let us see if we are able to find out the values for these A1, A2 and A3. So from the definition of scalar multiplication, we will get the following. We need to multiply the scalar A2 with all the elements. How did we get this line? This is from the definition of scalar multiplication. Then we need to add these matrices by the definition of addition. So we would get this. We got definition from addition. Now we need to solve this set of equations that we are getting. So what are the set of equations that we have? We have, setting this element to 0, we have A2 minus 2 times A3 is equal to 0, which implies A2 is equal to 2 times A3. Then what else do we have from this equation? We have A1 plus a2 minus a3 equal to 0, which implies a1 plus 2a3 minus a3 equal to 0. How we got this? I substituted this a2 equal to 2a3 over here for this a2. So then what do we get? We get a1 plus a3 equal to 0, which implies a1 equal to minus a3. So now this, so what are the conditions that we are getting? We are getting let us just write all the conditions that we have got. This is the condition that we have got. Clearly these elements are not 0, that is a1, a2, a3 are not equal to 0. All these three elements simultaneously are not 0. So that means that these three matrices are not linearly independent, which means that they are indeed linearly dependent. How we can say that? We can find out one particular example which solves this set of equations that we have. So a particular solution, let's say a particular solution to this set of equations would be, let us say a3 equal to 1, then we will get a1 equal to minus 1 and a2 equal to 2. This is what we will get as a particular solution. So what does this mean? This means that the solution to this equation that we started off with, the linear combination of the vectors, does exist. So solution exists, or non-trivial solution rather I should say, non-trivial solution exists. Non-trivial meaning all the elements are not 0. So a1, a2, a3 not equal to 0. And in particular we have seen one particular solution over here which says that this combination minus 1 plus 2 times the second vector plus the third vector gives me the 0 vector. So we can rewrite this, then we will see that the third vector can be written in terms of the other two vectors. So we are able to write one element from the set that we have, one vector from the set of vectors that we started off with. So this one element can be written as a linear combination of the other remaining two vectors that we have. So this implies that these three vectors are linearly dependent. Linearly dependent. So this is one particular solution that we have found out. In reality, there would be other possible solutions which would be just multiples of these. Say for example, if we took a3 to be equal to 2, then a1 would be minus 2, a2 would be 4. So just multiples of these values that we have, we will get if we choose different values for a3. So we have finally proved, rather we have shown that this set of vectors that we started off with, these three vectors, they are linearly dependent, and we have worked out all the steps to see that indeed they are linearly dependent. So this solves this question, and it brings us to the end of this video. this was a concept, the new concept that we saw in this video was linear independence and linear dependence.